um, transmission line parameters, that is resistance, inductance, capacitance, and some type of conductors, standard, solid, bundle conductors, then effects, that is skin effect, proximity effect, calculation of inductance for single phase, for three phase symmetrical, three phase asymmetrical, then calculation of capacitance, single phase two wire, three phase symmetrical, three phase asymmetrical, and effect of earth on capacitance, and also calculation of inductance for double circuit line, calculation of capacitance for double circuit line. These are all discussing in last couple of days. That is nothing but first unit of EPT, electrical power transmission system subject. Now today onwards I'm going for unit 2. So that is performance of transmission lines. So in performance of transmission lines, so first classification of overhead transmission lines. Generally, the important consideration in the design and operation of a transmission line are the determination of voltage drop, line losses, efficiency of a transmission line. So these values are greatly influenced by the line constants, that is R, L and C of the transmission line. For instance, the voltage drop in the line will depending upon the above three parameters, that is R, L and C. Similarly, the resistance of transmission line conductors is the most important cause of power loss in the transmission line and also for determining the transmission efficiency. Now in this unit, we have to develop formulas to calculate the voltage regulation mainly. So in total unit, second unit, you have to calculate voltage drop, to calculate voltage regulation for short transmission line, for medium transmission line and long transmission lines. And also efficiency, determine the efficiency, transmission efficiency and voltage regulation. Line losses. These formulas are very important for two principal reasons. First, they provide an opportunity to understand the effect of parameters of the line on the bus voltages and flow of power. Secondly, they help in developing overall understanding of the electrical power system. Generally, first, to represent the short and medium lines, first of all, we go for the classification of overhead transmission line, and then performance of short transmission lines, and then performance of medium transmission lines, and lastly performance of long transmission lines. Right? So first, classification of transmission lines. Generally, a transmission line has three constants, that is R, L and C, distributed uniformly along the length of the line. The resistance and inductance form the series impedance, right? The capacitance existing between the conductors of single phase line or from a conductor to neutral for three phase lines. That means it forms a shunt path. Resistance, inductance are a series in the transmission, but capacitance are in parallel. That is, it look like as a shunt branch or shunt path throughout the length of the line. Therefore, the capacitance effect introduce the complications in transmission line calculations. Depending upon the length of the lines, so the overhead transmission lines are broadly classified into short transmission line, medium transmission line, long transmission lines. When the length of the overhead transmission line is up to about 50 kilometers or 50 miles, whatever it may be, 50 kilometers or 50 miles, and the line voltages is less than 20 kilowatts, then only the type of lines are called as short transmission lines. So look at the figure. For short transmission lines, the voltage must be less than 20 kV or 33 kV. In general, 20 kV. And length is less than 80 kilometers or less than 50 miles. Such type of transmission lines are called as short transmission lines. It is usually considered as short transmission line due to smaller length and low voltages. The capacitance effect is negligible. So in these short transmission lines, because of low length, less than 80 kilometers or less than 20 kV or 33 kV, so the effect of capacitance is very low. That's why it may be neglected. Therefore, parameter calculated in short transmission line is nothing but resistance and inductance only, right? So therefore, while studying the performance of transmission lines, only resistance and inductance of line are taken into account, right? Next, medium transmission lines. When the length of the overhead transmission line is about 50 kilometer to 150 kilometers, 50 to 150 kilometers, and voltage is moderately high, that is greater than 66 kV or 132 kV. It is considered as medium transmission lines due to sufficient length. Here length is there 80 to 160 kilometers, right? And also greater than 160 kilometers, greater than 60 kV. Moderate voltage is there, moderate length is there. That's why the capacitance effect are taken into account. For the purpose of calculation of voltage drop and efficiency, we have to take into the account resistance, inductance and capacitance, and the line is divided into lumped network in the form of condensers shunted across the line. That's why medium transmission lines are broadly classified into nominal-pie, nominal-t methods. Nominal-pie, nominal-t methods. Last one, long transmission lines. When the length of the overhead transmission line is more than the 150 kilometers or 160 kilometers, right? And the voltages are greater than 100 kV or greater than 132 kV. That lines may be considered as long transmission lines. When the length of the overhead transmission line is more than 150 kilometers and the line voltage is very high, that is greater than 132 kV, it is considered as a long transmission line. For treatment of such long transmission lines, the line constants are considered as uniformly distributed over the whole length of the line, and rigorous methods are employed for the solution, right? For medium transmission lines, lumped network. For long transmission lines, uniformly distributed network. For the competition exams, it is most important. So this slide is most important for competition exams. For short transmission line, less than 80 kilometers and voltage less than 33 kV. And here capacitance is not considered. Medium transmission lines, distance is 80 to 160 kilometers, voltage is greater than 132 kV, sir, up to 132 kV. And here RLC are lumped parameters, whereas long transmission lines greater than 160 kilometers, greater than 132 kV. So RLC are here uniformly distributed elements, right? So very important. This is about classification of transmission, overhead transmission lines. Now, most important terms. That is in this topic, we have to calculate voltage regulation and also we have to calculate transmission efficiency, right? These two are the most important terms. That's why define, first of all, while studying the performance of a transmission line, it is desirable to determine the voltage regulation and the transmission efficiency. Now, first of all, voltage regulation. When a transmission line is carrying current, so whenever Conductor carrying current is nothing but some voltage drop is there, right? Voltage drop is nothing but V is equal to IR or IZ. It is AC, that's why IZ. Multiplication of current multiplied with product of current and impedance is nothing but voltage drop. When a transmission line is carrying current, there is a voltage drop in the line due to resistance and inductance, totally impedance of the line. The result is that receiving end voltage VR of the line is generally less than the sending end voltage Vs. Receiving end voltage VR is generally less than the sending end voltage. Why? Because, for example, so ఒక ఐస్ గడ్డ మనం ఇక్కడ నేను సంధ్యా చేతికిస్తే సంధ్య సుధీర్కి ఇచ్చి సుధీర్ లక్ష్మికి ఇచ్చి లక్ష్మి మళ్ళీ సువర్ణకి ఇచ్చేసరికి సువర్ణ దగ్గరికి వచ్చేసరికి ఆ ఐస్ గడ్డ కరిగిపోయి ఉంటుంది, రైట్? సంధ్యాకి ఇచ్చిన వోల్టేజ్ 230 volts అయితే సంధ్య దగ్గరికి వచ్చేసరికి అది 210 200 volts అవుతుంది. ఏమైంది మరి 20 volts? ఈ 20 volts is the drop, voltage drop. So many elements are there. Sudhir and Lakshmi are the elements, resistance and inductance elements. Because of that elements, voltage drop is there. That means reduction, losses is there, right? So we have to calculate that one. That's why sending end voltage 230 volts at the Sandhya's voltage 230 volts. Suvarna voltage is 200. That is the receiving end voltage, right? Receiving end voltage is always less than the sending end voltage. Receiving end voltage of the line is generally less than the sending end voltage. So this voltage drop, difference between these two voltages, Vs minus Vr, this voltage drop of the line is expressed as percentage of receiving end voltage Vr, and this is called voltage regulation. Percentage voltage regulation mathematically expressed as Vs minus Vr by Vr into 100, right? Vs minus Vr by Vr into 100. Generally, it is desirable that voltage regulation of transmission line as low as possible. Transmission efficiency means high ga undali manaku. Efficiency అనేది high ఉండాలి. హై ఉంటే మన లైన్ పర్ఫార్మెన్స్ బాగుంటుంది. అదేవిధంగా వోల్టేజ్ రెగ్యులేషన్ వాల్యూ తక్కువగా ఉంటే సో మన performance of the transmission line is very high. That is, increase in load current should make very little difference in the receiving end voltages, right? So this is the definition of voltage regulation. Difference in no load voltage to full load voltage, and it expressed as full load voltage. Next, transmission efficiency. The power obtained at the receiving end, power obtained at the receiving end of the transmission line is generally less than the sending end. Already discussed right now. Voltage తక్కువగా ఉంటే పవర్ కూడా తక్కువగా ఉంటుంది కదా. The power obtained at receiving end is always less than the sending end power due to losses in the line resistance. Therefore, the ratio of receiving end power to the sending end power of a transmission line is known as the transmission efficiency. Efficiency is nothing but output power by input power, right? Here output power is nothing but receiving end power, input power sending end power. So ratio of receiving end power to the sending end power of a transmission line is known as the transmission efficiency, and it is expressed in mathematically efficiency of a transmission line, receiving end power by sending end power into 100, right? So now this is the just what is the performance of transmission line, and what are the classification of transmission lines, and what are the important terms to calculate the transmission lines. Efficiency regulation. Regulation means difference between the receiving end voltage to sending end voltage, and it is expressed as percentage receiving end voltage. That is called regulation. Regulation always as low as possible for a transmission line. Similarly, ratio of receiving end power to sending end power of a transmission line is called transmission efficiency for a transmission line. So the efficiency must be as high as possible. Generally, what is the receiving end power? Receiving end power is nothing but VR IR cos pi r, right? VR, IR, receiving end voltage, receiving end current, receiving end power factor. VR, IR, cos pi r by sending end power means VS, IS, cos pi s into 100. That is the transmission efficiency. VR, IR, cos pi r by VS, IS, cos pi s into 100. Where VR, IR and cos pi r are the receiving end voltage, current and power factors, while VS, IS and cos pi s are the corresponding values at the sending end. Now go for the main topics, that is main topic in the syllabus, that is the first of all performance of short transmission lines, then performance of medium transmission line, then performance of long transmission lines. So second unit is closed, right? So out of these, performance of medium transmission, that is the most important one. They are asking derivation, they are asking problem also in medium transmission, and sometimes they are asking performance of single phase transmission line also, right? First we go for the performance of single phase transmission lines. So the effect of line capacitance are like neglected, right? In short transmission lines, length is less than 80 kilometers or less than 50 kilometers, right? Length is low and voltage also very low, less than 20 kV or less than 33 kV, right? That's why the effect of capacitance is neglected. Therefore, while studying the performance of short transmission lines, only resistance and inductance of the line are taken into account. The equivalent circuit of a single phase transmission line as shown in figure. Here the total line resistance and inductance are shown in concentrated or lumped loads, right? The circuit is a simple AC circuit, just resistance and inductance. So look at the figure, just resistance and inductance and load. This is the receiving end voltage VR and this is the sending end voltage, right? I am explaining phasor diagram later. Suppose they are asking question, explain the performance of short transmission line, means you have to write like this only. So this diagram and this phasor diagram and formulas for efficiency, formula for voltage regulation. That's enough, right? So there is no inductance here. There is no capacitance here for short transmission line. Why? Because distance is low, voltage is low. That's why capacitance is neglected. That's why there is no capacitance in the circuit. Only resistance and inductance are XL, sending end voltage, receiving end voltage, load, current. Where I is the load current, R is the loop resistance, and XL is the loop reactance, VR is the receiving end voltage, VS is the sending end voltage, cos pi R receiving end power factor, cos pi S sending end power factor. Why I am taking lagging? It is a inductive nature, that's why lagging. Just look at the phasor diagram. Look at the phasor diagram. Just we have to take as account receiving end voltage as reference. Generally, receiving end voltage as reference, VR as reference. It is a resistive network. So that's why pi R. So this is the I. Current is lagging, right? Inductive network, that's why current is lagging. VR is taken as a reference. Current is lagging by angle pi R. This is current and this is current lagging by VR with an angle pi R. Now here some drop is there and here some drop is there, right? IR drop, resistance is always in phase with current, right? That's why current elagundo gisamo IR drop kuda alane giyali. And this drop I into XL drop always 90 degrees for the resistance. That's why exactly 90 degrees. Now combination of VR, IR, IXL is nothing but sending end voltage. So VR, the drop in IXL plus drop in IR is nothing but sending end voltage. So the phase angle between sending end voltage and current is pi S. Phase angle between VR and I is pi R, right? Once again I explain clearly. First you have to take in reference as receiving end voltage. First draw the receiving end voltage, and current is lagging. Why? Because it is a reactive network, inductive network. There is no capacitance. That's why current is lagging with some angle by VR. Now draw the current I with the angle pi r. Now here two drops are there, resistive drop, inductive drop. Resistive drop always in phase with current. That's why I am drawing like this. And inductive drop is always 90 degrees above the resistive drop. Now combination of VR, IR, IXL is nothing but sending end voltage, right? So in this performance of transmission lines, circuit diagram and phasor diagram most important. Now we have to calculate the voltage regulation and power factor, all these things, formulas. So by using these formulas, we have to do the problems also. Suppose they asking question, explain the performance of short transmission means, you have to write all these things only, enough, just enough. At that time, circuit and this phasor diagram is most important. Look at the phasor diagram. From the phasor diagram, the lagging load power factor is shown in figure. From the right angle triangle ODC, look at the figure ODC, OC square is equal to OD square plus DC square, right? From the triangle OCD, hypotenuse square is equal to opposite square plus adjacent square. Here hypotenuse means OC square, adjacent means OD square, opposite means CD square, right? So like this. What is OC? OC is nothing but VS, right? VS square. What is OD? OD means, look at the figure phasor diagram. OD means OE plus ED, right? What is OE? That is VR. What is ED? IR. So OE plus ED square plus DC means DB plus BC. Look at the figure once again. OD is equal to OE plus ED. CD equal to CB plus DB, right? OE ante VR, ED ante IR, and CD ante IXL, OE ante VR cos pi r, OE ante VR cos pi r, ED ante IR, and CB ante IXL, DB means VR sin pi r. So look at this one. So OE VR cos pi r plus ED IR square plus VR sin pi r IXL square. Therefore VS is equal to square root of. So మీరు బాగా గుర్తుపెట్టుకోవాలి ఫార్ములా. Sending end voltage. Sometimes they are asking problem, calculate the sending end voltage. They given all these things. First we have to calculate the IR drop and IXL drop. Then we have to calculate the sending end voltage. Sending end voltage is equal to square root of VR cos pi r plus IR square plus VR sin pi r plus IXL square. We know the sending end voltage, we know the receiving end voltage. Therefore, percentage voltage regulation is equal to Vs minus VR by VR into 100. Now, power delivered. Power delivered means receiving end. Sending end power means sending end Vs. Vs Is cos pi s. Sending end power means that is VR IR cos pi r. That is the sending end power. Power delivered or receiving end power, whatever it may be. This is the VR IR cos pi r. Sometimes they are asking calculate the sending end power factor. At that time we don't know sending end power factor. That's why cos pi s. So from the triangle OD by OC. So from this cos pi s is equal to Cos means adjacent by hypotenuse, right? Adjacent OD by hypotenuse OC, right? OD by OC. OD, already this is the OD. OD means OE VR cos pi r plus IR by VS. Sending end power factor cos pi s is equal to VR cos pi r plus IR by VS. Power delivered VR IR cos pi r. And power send VR IR cos pi r plus copper losses I square r. Therefore, we know the output power delivered, we know the input, we know the losses. Therefore, transmission efficiency is equal to power delivered by power sent. Power delivered. So this is the power delivered VR IR cos pi r. The power sent, this one VR IR cos pi r plus line losses I square r. So output by output plus losses, that is the transmission efficiency. In this way, we have to calculate voltage drop, sending end voltage, and sending end power, line losses, transmission efficiency, right? Now, how to calculate this is for single phase, right? Performance of single phase short transmission means. Suppose they given three phase, how to calculate it? So for that, for reason associated with economy and transmission of electrical power is done by three-phase system. The system may be regarded as consisting of three-phase circuits, each wire transmitting 1/3 of the total power, right? As a matter of convenience, we generally analyze the three-phase system by considering the single phase only. Therefore, expression for regulation efficiency derived for single phase line can also apply to three-phase system, right? First of all, you have to calculate the single phase regulation efficiency. First of all, we have calculated three single phase, and then that may be applied to three phase also. Vs, Vr are the phase voltages, and R, XL are the resistance inductive reactance for phase only. Here, sending end voltage Vs and sending and receiving end voltage Vr are these nothing but phase voltages, and the resistance and XL also phase values. After calculating the phase values, that may be applicable to three phase only. Here, the figure shown. So this is look at the figure. Figure shows a star connected generator supplying a balanced star connected load through a transmission line. Each conductor has a resistance of R ohms and inductive reactance of XL ohms. Sorry for the disturbance. Power problem, Sandhya. Just
Sir,
wait for 2 minutes.
okay, sir.
పవర్ పోయి మళ్ళీ వచ్చిందమ్మ ఇప్పుడే. Look at the figure. So first figure will shows the star connected generator supplying a balanced star connected load through a transmission line. Each conductor has a resistance of capital R ohms and inductive reactance of XL ohms. Now figure 2 represents the per phase separately. So this diagram is per phase, second diagram is per phase, and this is the three-phase system, first figure. Now first we have to calculate the per phase values, and then that may be applicable to three-phase only. The calculation can now made in the same way as for the single phase line only. So right, suppose you have to calculate the three-phase means first calculate the single phase and then applicable to for three-phase. So this is for short transmission line, and next go for the medium transmission lines. So this is also a short transmission line calculations. Effect of line capacitance are neglected, right? Because length is less, that's why capacitance may be neglected. Why? Because voltage also less than 20 kV and length also less than 80 kilometers. However, the length and voltage of the line increases, then the capacitance is gradually becomes greater importance. Since medium transmission lines have sufficient length, 50 to 150 kilometers, and operating voltages greater than 20 kV, therefore the effect of capacitance cannot be neglected. Therefore, in order to obtain the reasonable accuracy in medium transmission line calculations, the capacitance must be taken into consideration. Capacitance is uniformly distributed over the entire length of the line. However, in order to make the calculation simple, the line capacitance is assumed to be lumped or in concentrated in the form of capacitors shunted across the line at one point. Such a treatment of localizing the line capacitance gives reasonably accurate results. The most commonly used methods for finding the capacitance of medium transmission line is first method is end condenser method, second one method is nominal-t method, third method is nominal-pie method. First method is end condenser method, nominal-t method, nominal-pie method. So out of these three, last two, nominal-t, nominal-pie, most important, complete important in second unit. They are asking problem, they are asking theory, right? So design T and pi networks. They given ABCD parameters. They then design the T and pi network, right? So end condenser method, nominal-t method, nominal-pie method. These are the main methods to calculate the voltage regulation and transmission efficiency in the medium transmission lines. So these methods may utilize to calculate the performance of transmission lines, even though short transmission line also. But in short transmission lines, line capacitance is neglected. That is the only thing. So first method is end condenser method. That is the first method. So after this method, I am closing the class, right? Most important methods, that is pi method and t method, I may explain next class. End condenser method. Look at the figure. So in short transmission line, there is no capacitance, right? Only sending end voltage, receiving end voltage, resistive drop, reactive drop is there. But coming to the medium transmission lines, so effect of capacitance is considered, and it may be shunted across the load circuit. So in this method, capacitance of the line is lumped at the receiving end as shown in figure. This method of localizing line capacitance at the load end overestimate the effect of capacitance. First figure, this figure shows the single phase of the three-phase transmission line, and it is more convenient to work in phase instead of line to line values. So నేను ఇందాక ఆల్రెడీ చెప్పాను, త్రీ ఫేజ్ క్యాలిక్యులేట్ చేయాలంటే ఫస్ట్ సింగిల్ ఫేజ్ క్యాలిక్యులేట్ చేయాలి, అది ఫేజ్ టు ఫేజ్ వాల్యూస్ క్యాలిక్యులేట్ చేసిన తర్వాత దెన్ లైన్ టు లైన్ క్యాలిక్యులేట్ చేస్తాం. సో హియర్ లెట్ IR is the load current per phase, R resistance per phase, XL inductive reactance per phase, C capacitance per phase, cos pi R receiving end power factor, lagging, load is lagging, that's why receiving end power factor is always lagging. Next VS sending end voltage per phase, right? Now I am explain the phasor diagram as usual, similar to that of short transmission line. ఏం చేసాం, షార్ట్ ట్రాన్స్మిషన్ లైన్లో ఫస్ట్ రిసీవింగ్ వోల్టేజ్ని రెఫరెన్స్గా తీసుకొని కరెంట్ ల్యాగింగ్ కాబట్టి దాని కింద బిలో గీసేసి ఇప్పుడు ఏమేమి డ్రాప్స్ ఉన్నాయి, రెసిస్టివ్ డ్రాప్ ఉంది, ఇండక్టివ్ డ్రాప్ ఉంది. అక్కడ రెసిస్టివ్ డ్రాప్ అనేది ఆల్వేస్ కరెంట్కి ఇన్ ఫేజ్లో ఉంటుంది, రియాక్టివ్ డ్రాప్ 90 degreesలో ఉంటుంది. వాటిని కంబైన్ చేస్తే సెండింగ్ ఎండ్ వోల్టేజ్ వచ్చింది. బట్ ఇక్కడ 3 డ్రాప్స్ ఉన్నాయి, రెసిస్టివ్ డ్రాప్ ఉంది, ఇండక్టివ్ రియాక్టివ్ డ్రాప్ ఉంది, కెపాసిటివ్ రియాక్టెన్స్ డ్రాప్ కూడా ఉంది. Just observe that one only. I am explain the phasor diagram. So I am not showing this. VR is taken as reference phase, taking the receiving end voltage VR as reference phasor. That means VR is equal to VR plus J0, and IR is the receiving end voltage that is lagging with some angle, that is pi R, same as before phasor diagram. And ISR is same as IR, and ISXL is 90 degrees. Now combination of VR, ISR and ISXL is nothing but sending end voltage, where IS is nothing but, here look at the figure, sending end current is a combination of capacitive current and receiving end current. IS is equal to IR plus IC. IR means IR cos pi R minus J sin pi R. IC means capacitive current, V by XC, that is 1 by 2 pi FC, 2 pi FC VR. So taken as IR cos pi R common factor and J term as common factor. Therefore voltage drop is equal to IS into Z is equal to IS into R plus JXL. Sending end voltage is equal to VS is equal to VR plus ISZ, that is VR plus IS. Z means R plus JXL. Therefore we have to calculate the sending end voltage, after then voltage regulation. Voltage regulation is equal to difference between the sending end voltage minus receiving end voltage by expressed receiving end voltage. Vs minus Vr by Vr into 100. Then percentage voltage transmission efficiency, that is power delivered per phase divided by power delivered per phase plus line losses, that is VRIR cos pi r by VRIR cos pi r plus I square IS square r into 100. Even though the end condenser method having some disadvantages, although this is simple method to calculate the voltage drop, to calculate the efficiency for medium transmission line, it is a simple method. End condenser method is simple method. Even though it is simple, it will having some limitations. There is a considerable error, just about 10% error is there for calculation of voltage drop and efficiency, because the distributed capacitance has been assumed as lumped network. That's why some percentage error will be available. Next, this method is overestimated the effect of capacitance. Because of overestimation of capacitance, more losses occurred. Right? This is about end condenser method. Next class, I discuss about the nominal-t method, nominal-pie method, most important, right? And also calculating the ABCD parameters in the nominal-pie method, nominal-t method, right? So that is the most important. Next class is the most important. Any doubt? ఏమైనా డౌట్ ఉంటే అడగండి అమ్మా.